Okay, I'm going to, in this lecture, I'm going to actually skip quite a bit of really beautiful analysis on master equations and the conversion of those into Fokker-Planck equations. And we will just basically outline the strategy in words of what's happening in this part of the classical nucleation theory. There's a lot of beautiful work out there, but in the interest of making interesting videos, and I'm under no illusions that my videos are really that interesting anyway, but still, it would be pretty painful, I think, to go through all of that in a video. So I'm going to skip it and just outline for you how it goes and how it's related to the stuff that we've done in previous videos. So we have already talked about the free energy of classical nucleation theory and how it relates to the equilibrium population distribution of nuclei of different sizes, even though that equilibrium population distribution is not properly normalizable, and all those caveats aside. So we could write it down, and within some constant that we can never find, it exists. Okay, so now what we want to do is to think about how, we have nuclei of size 1, 2, 3, 4, and if they're not in equilibrium, we want to be able to describe, using basically ideas that look just like continuity equations, how that distribution will evolve in time until it gets to, until it reaches its equilibrium distribution. Okay, so now imagine, in order to do that, we have to have a prescription for the dynamics of state-to-state transitions. Okay, so we have nuclei of size n, and they can combine with monomers, and that combination gives rise to a nucleus of size n plus 1. And the rate constant for that combination is this beta sub n constant here. So also our nuclei of size n plus 1 can shed one monomer and go back to a monomer and a nucleus of size n again. Okay, so in classical nucleation theory, this is the only kinds of ways that the nucleus can change size is by addition or loss, that is attachment or detachment of one single monomer out of the solution. Okay, so for this is a so-called one-step process, and you can pretty easily go through and write down a master equation to describe how the population of nucleus sizes will evolve in time if you start from any given starting distribution, right? So now what we're going to do in the classical theory is we're going to take that discrete master equation. We could follow Becker and Doring and actually try to solve that master equation discretely, and you can do that actually exactly. But what we want to do to get a sort of useful and nice physical interpretation of what's going on is to instead treat nucleus size as a continuous variable. That is to assume that the differences in the properties of nuclei of size n and those of size n plus 1, including the differences in these rate coefficients for changing size, are actually not changing so rapidly and dramatically as a function of the nucleus sizes that they describe. So if we can do that, then we can begin to differentiate these quantities as a function of n, and now our master equation becomes a Fokker-Planck equation of a special type called Zeldovich-Frenkel equation that's written here. Okay, so all of that analysis would take a chapter to go through and explain, and it's going to give you this. Okay, so this is the Zeldovich-Frenkel equation, and you'll notice here that it's been written in this form where I've got a non-equilibrium time-dependent population distribution. This is a function of nucleus size and time, and here it appears on the right-hand side of the equation as well. But here it's normalized by the equilibrium at the same size. So here I've got rho of n and t divided by rho eq of n. Okay, and notice that we're differentiating these things with respect to nucleus size. In fact, we're differentiating them again, so these have to be smooth functions of nucleus size as a function of time. All right, my slides are not working. Okay, so now what we're going to do is we're going to define this ratio, non-equilibrium to the equilibrium, as a so-called Kramers crossover function, this phi function, and that's again going to have to be a function of nucleus size and time, and we'll now write the Zeldovich equation in terms of this phi. Okay, so we have to multiply and divide by rho equilibrium wherever we need it. For example, on the right, we will multiply and divide by that rho EQ, and then be able to write this as a time derivative of the phi. And after going through and doing some of those really elementary chain rule kinds of operations, following through all of these derivatives with n and t, we find a Smolakowski equation. Okay, so the Smolakowski equation is just a special Fokker-Planck equation that does not include any momentum variables, and it includes, it's a broad class of equations that includes things like this Zeldovich-Frenkel equation. And what you recognize, so perhaps I should say one other thing about the Smolakowski equation, is that you can think of it as describing diffusion in a potential of mean force. Okay, so the potential of mean force here is our free energy landscape. It's a function of nucleus size, this free energy, and we have and we also have a mobility, and that's our diffusion constant. Okay, so the diffusion constant in principle, in general, can depend on nucleus size, and we usually expect, in fact, that the rate at which you add monomers is proportional to the surface area of your nucleus is a quite common model for this thing. So we do expect this diffusivity to be a coordinate-dependent diffusivity. Now what we're going to do is look through this equation and recognize that actually I replaced this beta by diffusivity here. And the reason that I did that is because the beta, that is this coefficient for going forward from the n mer to the n plus 1 mer, it appeared in the Smolakowski equation in exactly the normal place where this diffusivity is. And that's actually no coincidence. If you think about a nucleus growing and shrinking by attachment and detachment of single monomers, those look like steps in a random walk. They're either forward or they're backward along the nucleus size axis. Okay, so you can imagine now this nucleus not stepping in physical space, but stepping in a space that represents its size, doing a random walk along maybe the top of the barrier until it falls off. And this is actually a way, using simulations, that you can compute that diffusivity parameter. So this is work done by Molinaro and Mike Doherty. The graduate student doing this was Brandon Knott. And so you have a mean squared displacement as a function of time. And if you plot those, you get a straight line. You can fit that straight line to this curve. 2 times displacement times time is mean squared displacement. Extract from that this diffusivity near the top of the barrier, and that will be a key parameter in our nucleation rate theory expression later in this talk. Okay, so remember that its physical interpretation is this random walk in nucleus size by attachment and detachment steps. So effectively, this parameter d includes both our forward and backward, but the backward have to be consistent with the forward through detailed balance. So if we know the difference in the free energies of two states and we know the forward step rate, then we don't actually need to keep the alphas. And because beta usually to statistical mechanics people means 1 over kt, we replace everything by diffusivity. And so that's where we stand with our notations here. So we have an equation that describes the population evolution evolving in time, and we're getting closer to having a rate constant, but we're really not done yet. So notice that if you have changes in nucleus size down near the bottom of the barrier, the system is very unlikely to cross over to the top of the barrier, and so it will likely just be forgotten, right? And if you go far past the barrier, you're never going to come back. You're basically going to start just nucleus growth or crystal growth, I should perhaps say, because it's basically deterministic from that point, and we can actually solve equations to describe the crystal size and shape as a function of time. So all of the really interesting action, the stochastic process, if you want, that's going to determine whether our nucleus grows or shrinks, is all happening near the top of the barrier. And near the top of the barrier, we're going to do the usual thing, and we're going to approximate the shape of the free energy profile as a parabola. Okay, so this is just a Taylor approximation. Normally you would see a 1/2 times the second derivative of the free energy with respect to n here, and then multiplied by the squared displacement from the top of the barrier. That's this delta n squared. So, in fact, if you plug in this definition of z, so this is a rather unusual looking coefficient here, but if you plug in this definition for z, this is this Zeldovich factor, you will see that there's a lot of cancellation, and indeed this thing becomes a Taylor approximation to the free energy as a function of nucleus size at the top of the barrier. Okay, so remember this guy, this Zeldovich factor. We've rewritten the equation in this way because it will turn out to be quite convenient to define this z later in the theory when we actually compute the rate. Okay, so now we have a steady state Smolakowski equation that describes the non-equilibrium relaxation of a population of nuclei of non-equilibrium sizes towards equilibrium. And what we're going to do is we're going to actually solve this for steady state conditions. Okay, so we're going to actually find a non-equilibrium steady state for which the equilibrium and the non-equilibrium match for the precritical nuclei. Those are for the nuclei much smaller than the critical nucleus size, and where the equilibrium is doing what it will over in the postcritical sizes, but we actually assume that we don't have any nuclei there yet. And this comes about if you can imagine the physical scenario where you have a metastable condition, and every time a nucleus forms, you're going to pick it up, dissolve it back into solution, and put it back into the metastable state. And if you could do this repeatedly, then what you would have is a steady state current leaking out of the metastable basin over the barrier and going on to growth. So this is this current. This is effectively the rate that we want to find. In order to find it, we have to solve for this steady state distribution under these rescue and replace kinds of boundary conditions. So these are the boundary conditions that correspond to that scenario. I want the system to resemble a quasi-equilibrium when it's in the metastable state, and I want it to go to zero. This ratio of non-equilibrium to equilibrium should go to zero when I'm in the post-critical sizes. Okay, so that kills off the time-dependent term in our equation because we're looking for a steady state. This term then vanishes because there's a zero on the right-hand side, and this, of course, is non-zero. Integrating the first time with respect to n just gives us a constant. So now we can set all of this stuff inside the parentheses here equal to a constant, and we find that phi steady state then, because the free energy here is a Gaussian, and because we assume this diffusivity is roughly constant near the top of the barrier, we can find that this steady state non-equilibrium ratio of population distributions is just 1/2 of the error function complement. There's the Zeldovich factor times the square root of pi, and this is the deviation from the critical nucleus size. So this thing basically looks like a sigmoid function. It's going from 1 on the left of n dagger, and then as it crosses through n dagger, it passes through 1/2. So when the RFC is 0 here, we're at 1, and that makes this phi steady state 1/2. It's the committer equals 1/2 point, if you want to think about this in the language of transition path theory, and then if you cross over to where n is much greater than n dagger, this thing does what it's supposed to do and goes to 0. Okay, so this is our steady state distribution. It's going to allow us to predict this current passing over the barrier to the product state. So now we are in position to do the calculation. We know that our current, our nucleation rate constant, if you want, is the rate at which nuclei move around on top of the barrier. That's this mobility factor, times the gradient in the steady state concentration at the top of the barrier, right? So it's a gradient with respect to nucleus size at the top of the barrier. Now, take a look at these two distributions. I've sketched them over here. This is the steady state distribution, and it's a rather inconvenient thing to work with. We prefer to think about this equilibrium distribution because, of course, it has this nice physical interpretation just in terms of the interfacial free energy and driving force parameters that we saw in a previous talk. Okay, so this is the equilibrium population of nuclei as a function of nucleus size here, and you see that it passes through a minimum. This is the rarest of all nuclei, is right there at n double dagger. This is my critical nucleus size, and it really doesn't enter into this picture at all, right? We've got an intrinsically non-equilibrium steady state calculation that we're doing, but what we're going to do is we're going to write the steady state nucleation rate in terms of the equilibrium probability to be at the dividing surface. And the reason that pops out is because this is the thing that we want the gradient of, but this is the thing that we solved for. And of course, the equilibrium population, if I multiply this by this, I get back my rho steady state. Okay, so basically now just doing some math and using the definitions that we've already established on the previous pages, this thing turns into this formula. I've got a population of my monomers. I've got a mobility of those critical nuclei along the nucleus size axis. I've got a Zeldovich factor, which then allows me to write the gradient of the non-steady state distribution in terms of the probability of being at the top of the barrier, which is this e to the minus f of n dagger over kt. Note the structure of this formula. This is actually literally giving you the population of critical nuclei, right? So I've got the mobility factor here. Zeldovich is converting between this kind of derivative and the equilibrium probability. And if I take these things, rho 1, and I multiply by this exponential, remember that this exponential of Fn minus F1 is the ratio of nuclei of size n double dagger to nuclei of size 1. Then I multiply by nuclei of size 1, and what do I have left? I have the population of critical nuclei, right? So if I know the population of critical nuclei in my system and I multiply by the Zeldovich factor, multiply by the mobility, that gives me the rate. Okay, so that's why we introduced the Zeldovich factor. It's just a convenient notational summary that allows me to compactly write the result of this derivative. Okay, so what you have here is a nucleus that is a nucleation theory, a rate expression for nucleation that can be written as a prefactor multiplied by this exponential term. That exponential term has a remarkably simple form. It is a 4 times a dimensionless number to a dimensionless number that's cubed in this case, another dimensionless number, and that is the interfacial free energy times the interfacial area coming from the shape factor, divided by kt. We cube that, and we divide by 27 times the log of the supersaturation squared. Okay, so this is a really, really simple way of writing everything down so that you can really see what's happening here. I've got a term, my size of my barrier is modulated by the interfacial free energy and the area per volume, time divided by the temperature, and then I cube those things. So slightest change in the interfacial free energy causes a big change in the size of this barrier. And also, the slightest change in the supersaturation also causes a big change in this barrier. Okay, so we typically remember, right, that this delta mu, this driving force term, this would usually be delta mu squared on the bottom, is the log of s. Actually, that is missing a kt. Sorry about that. That should have a kt in front of it. It's correct in this formula, and it's correct down here, but I think there's an error right there. Okay, sorry about that. Okay, so now, depending on the attachment kinetics, right, so we've got this abstract mobility factor here, and that mobility, the rate of attachment and detachment is what it reflects, remember, and that depends on whether the attachment kinetics are diffusion controlled or surface reaction controlled. And they give rise to 2 different rate expressions. One of them, the diffusion controlled case, depends on the actual spatial diffusion. This is now meters squared per second normal diffusivity in solution. And it gives you a supersaturation dependence of the form S log S. Now this is in the prefactor, right? So in this prefactor term we have built in, because of the way the attachment kinetics depend on supersaturation, comes out to be S times the log of the supersaturation. And if you have, for example, in the case of a zeolite nucleation problem, where you have to actually have a condensation reaction in order to bring a silicic acid unit in and attach it to a growing nucleus, that is going to be surface reaction controlled, and probably many other processes are also surface reaction controlled. And that gives rise to a prefactor that can be written in this form, and it has a supersaturation dependence that's just S. Okay, so the regime that you're in sort of tells you how to scale J before taking the log of J and trying to extract these dimensionless parameters for understanding the barrier height and other things that are predicted in here. Okay, so again, I want to thank my sponsors. The NSF has sponsored us with a career award and also with a computational discovery and innovation award. This one is joint with Val Molinaro and Amadeo Sum and David Wu at Colorado School of Mines. And we have also support from the UCSB MERSEC as part of IRG3. with Teresa Pollack and Ram Shashadri, so we're thankful for that. And the Los Alamos Institute for Multi-Scale Material Studies has sponsored a project with Dan Hooks looking at nucleation in molecular systems. Of course, we are eager to get industrial sponsors as well. We have none at this time. And for a review on this stuff, you can see Vishal Agarwal and Baron Peters have a review coming out in 2013 that specifically addresses solute precipitate nucleation. That's in contrast to many of the previous reviews in this area, which mostly focus on things like Lennard-Jones fluids and supercooled water and things of that sort, single component structural transitions. We're really focused on the solute precipitate nucleation process. And you can read a lot more about this stuff on our website and the papers that you find there.